Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on December 1st, 2025, about a week ago. It argues that generative control policies in robots succeed not because they model fancy multimodal action distributions, but because they use supervised iterative refinement with just the right amount of injected noise. And it shows that a tiny two-step policy can essentially match much heavier flow-based controllers. The paper is titled, Much Ado About Noising, Dispelling the Myths of Generative Robotic Control. And, as we will see later, the implications for how we design future robotic policies are pretty significant. Also, the authors shared a GitHub repo that packages everything into an optimized PyTorch framework for behavior cloning with flow-style generative models. You will find modular training code, example scripts for RoboMimic, Kitchen, and push-T tasks, configuration files, evaluation routines, and hooks to load pre-trained checkpoints, plus documentation to tweak objectives and hyperparameters. Alright, Figure 1 pulls these ideas together by showing what really matters in these generative control policies. The left panel lists popular hypotheses, like pixel-based control and multimodal data, and it shows that only manifold learning clearly survives their tests. The middle taxonomy panel introduces 3 ingredients: distributional learning, stochasticity injection, and supervised iterative computation, and it highlights that policies combining the last 2 sit near the successful flow models. The right bar chart reports relative success rates, where the simple 2-step minimal iterative policy essentially matches flow, while plain regression and single ingredient variants lag behind. Well, Figure 2 puts numbers behind that claim by comparing regression and flow policies across dozens of benchmarks. The teal bars show flow performance, which is normalized to 1, and the gray bars show regression, plotted as relative success. Most gray bars sit almost at 1, so plain regression with the same architecture essentially matches flow on many image, 3-dimensional, and vision language action tasks. Only a handful of state-based insertion-style tasks fall below the red dashed 95% line, where flow still keeps a noticeable edge. Okay, Table 1 tests whether the way the flow policy samples noise actually matters for control performance. For push-T, Kitchen, and toolhang, the success rates for zero noise, random Gaussian noise, and the mean over many noise samples are all within a few percentage points. That tiny spread shows that picking a single deterministic action, like the mean, barely hurts performance, which strongly argues against the presence of clear, separated action modes in these tasks. So while Table 1 argued that multimodal sampling is not crucial, Figure 5 tackles the idea that iterative policies are more expressive. The left ground truth panel shows an extremely wiggly sine 1 over x function that has very high frequency detail. The regression panel in the middle simply smooths those wiggles away, because the network falls back to averaging. The flow panels add randomness, so the curve turns into a noisy band rather than a sharper fit. The minimal iterative policy on the right looks similar to regression, which confirms that these iterative generative controllers do not magically overcome the backbone's spectral limits. Alright, Table 4 compares how different policies perform on the multitask LEBRO benchmark. The rows show regression with L2 loss, regression with L1 loss, flow, and the minimal iterative policy across object, goal, spatial, and LIBRO10 suites. Flow slightly leads on LIBRO object with about 97% success, but minimal iterative policy is within a couple of points everywhere and actually wins on LIBRO10 with 82%. This pattern reinforces that a tiny 2-step iterative controller can match or beat heavy flow models, even in large-scale multitask settings. So, Table 6 digs into why minimal iterative policy and flow work so well by measuring how closely their actions stay on the expert manifold. The off-manifold errors, which capture how far actions drift on perturbed states, are clearly lowest for minimal iterative policy and flow across both original and deterministic datasets. The validation errors, which reflect simple reconstruction on held-out expert data, stay similar for all methods, including plain regression. This contrast shows that success comes from better behavior on out-of-distribution states, not from slightly lower reconstruction loss. Well, Figure 11 explores how both architecture and model size shape the comparison between regression, minimal iterative policy, and flow controllers. The 2 left panels show that no single architecture dominates, since regression sometimes wins with simple MLP or recurrent networks, while flow and minimal iterative policy fare better on transformer-style backbones. The right panels show that all methods improve with larger models, but regression saturates earlier, so minimal iterative policy and flow gain a clearer edge at high capacity. This pattern means that fair comparisons really require matching both backbone type and parameter count across methods. So the big message is that generative controllers shine not because they sample rich action distributions, but because supervised iterative refinement plus a bit of noise gives a powerful inductive bias towards staying on the expert manifold. That insight opens a design space of much lighter, cheaper robotic policies. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.